we're going to go in through to the area of a sector of the circle. So if I want to know the area of a sector, then the formula is equal to my angle. Angle has to be in radians. And then r squared divided by 2. So again, if I am trying to find the area, my angle alpha right here must be in radians. So that's alpha. Alpha times my radius squared divided by 2. So here, when I'm coming down here, on these examples, so example A and B, I have to make sure I am in radians. If I'm not in radians, then I have to do that conversion, and then I just put it in the formula. So go ahead and do A and B, make sure you convert into radians, and I'll come around and see how everyone's doing. What do I get? So I know that 30 degrees is pi over 6. So, and if I'm not sure, then what I do is the conversion I have is 30 degrees multiplied by pi 180 degrees. And that's where the pi over 6 comes from. So my area is equal to my angle, which is pi over 6, multiplied by my radius squared, which happens to be 6 squared, and then divide that all by 2. So what I end up with is I'm going to get pi over 6 multiplied by 36 over 1 divided by 2. The only reason I'm doing this is because I'm required to find the exact answer, so I want to do some cancellations. So the 6 and the 36 will cancel themselves out, and I'll end up with a 6 in the numerator. So I have 6 pi divided by 2, and my answer ends up being 3 pi. And then if my radius was in centimeters, my answer would be in centimeters squared. So I don't know what it is, so I'm just going to write units squared. I don't know what it is. It's in some sort of units. If I knew the radius, because the radius should have been in a unit of some form, then I would have had the answer in that unit. So I don't know it, so I'm just going to write units squared. Right?
Why?
I don't know what, because area is going to be whatever the units are squared, and I wasn't given units, so I just write units squared because I don't know what it is. So I'm just going to write units squared. If my radius was given to me, if that was given to me in centimeters, then my answer would have been in centimeters squared. If my units would have been in feet, my answer would have been in feet squared. Yes?
If you don't give a measure and you leave out unit squared, you get dot.
On the test, yes, units are worth 1 point. And so I'll tell you that on the test, though, I give you units. Units are worth 1 point, so units are important. Make sure you put units on all of your answers on the test. Units are important. On the next example, on B, it's already in radians, so I can go right to my area. So my area is equal to, I have my angle, which is already given to me in pi over 12. Then I have 8 squared, and then divided by 2. So I have 8 pi over 12, and then I'm going to multiply by 64 over 1, and then divide that whole thing by 2. The only reason I'm doing this, again, is because I'm asked for exact. If I wasn't asked for exact, I wouldn't do all these shenanigans. I'd just put in my calculator. But since it does ask for exact, then I have to do all of this extra work. So I'm going to cancel down my 12 and my 64. What is the largest number that goes into both 12 and 64? 4. 4 goes into 12 3 times. 4 goes into 64 16 times. So where I am now is 16 pi over 3 divided by 2. So I have a fraction divided by a fraction, so I have 16 pi divided by 3 multiplied by the reciprocal of the bottom fraction. Even though it's an integer, it really is a fraction by putting it over 1. My final answer when I get done on this, because my 16 and my 2 will cancel, my final answer when I get done is going to be 8 pi over 3 units squared. Again, if that was in feet, I would have said it's feet squared. If it was in miles, I would have said miles squared. How was that? Okay, cool. You know, if you've ever had the joy of flying over eastern Washington and you see all the circles, right? You see all the circles where they're all green. That's because you're irrigating the crops in circular patterns. Back in the day, they used to do the long way, but then they discovered that if they put it in a circular pattern, they can just let it go and they don't have to keep rolling it themselves. Have you all seen those? Someone was like, no. So if you ever fly over eastern Washington and pretty much everywhere in the Midwest, they irrigate their crops in rotational circles. So it's all circles now instead of, square. You'll see the crops are not square anymore, they're circular. So here's an example in which you're going to need to know how much is watered in 1 hour. So if you're like, man, I want to be a farmer, which is cool. We always need farmers. You'll be able to determine how much is going to be watered. So please do this one. Now, for this example, I don't want an exact answer. I just want to know how much is watered in 1 hour. Okay? And that's going to depend on how much is rotating in the hour. How much is rotating in the hour? 30 degrees. So go ahead and do that one. So after you've converted the degrees into radians, where it's 30 degrees is equal to pi over 6, you just throw this into the formula, and I have 150 feet is the radius of my crop, and so I have pi over 6, 150 squared divided by 2. Now, this would make sense to give it an approximation, because it would make no sense if you're going to tell a farmer, by the way, this is how much area is done in pi. That would make no sense. You wouldn't talk to anyone normally like that, so you wouldn't leave answers like this in pi unless it says exact, which is unlikely. When you did this, what did you get rounded to 2 decimal places? We got some 5,000s. Do you all agree? So 5,000. 5,890.49. So 5,890.49 feet squared. Yes. Yes, per hour. But we only want to know how much area is done, and so the answer is just that. If they wanted to know the rate, it is definitely by hour, per hour. Well, because the units they're not asking you what is the rate of watering, they're just asking you how much was watered. Good question, though. Okay, we have another conversion. Have you all had an opportunity to open up the formula sheet that I provide for every test? Do you all know where to find that formula sheet?
Yeah, where is that?
Okay, just a minute. We're going to do some angular and linear velocity, and then we'll have finally put 10.1 to bed. I would highly recommend that you start the homework on this already, because the homework should follow what we've done so far. So please don't wait to start 10.1. There's a lot in 10.1, and I want you to understand it. So please consider doing the homework starting right after class, even though we haven't finished 10.1, and go as far as you can. Have a great day. In my example, I didn't need to worry about it, but on this one, you do need to worry about it. So the question is on B, it says 3,000, but I don't see pi in there. Pi's already embedded in there. So some number times pi is 3,000. Remember, we're trying to convert from radians into revolutions. for those of you in the last two rows, it's not that I'm ignoring you, I'm just moving on, and I'll come back and ask questions if you have questions. So, okay, so on this problem, the first thing you want to do is do the conversions from radians per hour into hours per second. So for every hour, there's 3,600 seconds. So I have 1 hour over 3,600 seconds. And then I do my revolutions per radians. When I do that, I see my radians cancel. I get my hours cancel. And I end up with 3,000 over 3,600 times 2 pi revolutions per second. I put that in my calculator, and I get 0.1326 revolutions per second.
So are you multiplying 3,600 by 2 and then dividing that into 3,000?
So the question was, do I take the 3,000 and then divide that by 3,600? Because this is a string of multiplications and divisions, I can do 3,000 divided by 3,600, and then I divide that answer again by 2 times pi. Or I can do 3,000, and then first I'll do the 3,600 times 2 times pi. So if you put it in your calculator incorrectly, it's not going to read it correctly, but the order doesn't really matter as long as you've got everything in the right places. And what I mean by that is, if you put this in your calculator, you need to put it in 3,000 divided by parenthesis 3,600 multiplied by 2 multiplied by pi parenthesis.
Okay.
Because if you don't, if you do this, if you do 3,000 in your calculator divided by 3,600 times 2 times pi, your calculator is doing that.
Yeah, because I think the mistake I made was 3,000 radians. I thought, because you said pi was embedded, I thought that was 3,002 times 2 pi.
Unless you physically see pi there, it's embedded in there. There's some number times pi is 3,000.
Okay.
Yep, so some number times pi is 3,000. Moving on to angular velocity. This W is called omega. And so this is omega. And the angular velocity is simply how far did you revolve in the time that I'm asking you to do that. So the revolutions, how far did you revolve in terms of angular, is alpha. So you do need to make sure that you are in radians. All of these are in radians. If you wanted to know how far of an angle you revolved, you would just do omega times t is equal to alpha. So if you're looking for alpha, then you would do that. If you're looking for, if you're looking for the time it takes, then you do your alpha divided by your omega. So if you want to know how long it took in terms of your angle, you have the angle that's given to you, and you have the angular velocity, and you just want to know the time, then you do it that way. It's kind of like the rate times time equals distance type formula. We can just keep moving stuff around until we get to what we want. So the first one is a radar antenna makes 1 revolution in 2 seconds. What is its angular velocity? So how far of an angle is it if I do 1 revolution? 2 pi. So if I do 1 revolution, that's the same thing as 2 pi. And if I'm not sure, I can use the fact that I have that unity fraction. I have 1 revolution is equal to 2 pi radians. So I have that. 1 revolution equals 2 pi radians. I want to know what the angular velocity is, so they're asking me for omega. Omega is my angle divided by how long it took. In this case, it is 2 seconds. So my answer when I get done is just pi divided by pi radians per second. Pi radians per second. So any questions on that one? All right, go ahead and do the windmill. The first thing you want to do is read through it. Do I care about the fact that this blade is 30 feet? No. Not for this one, no. So I really don't need that information. All I need for angular velocity is I need the angle, and I need to know the time at which it goes takes to do that angle of rotation. So I have to convert 90 degrees into its radians. So what is 90 degrees in terms of radians? So it is pi over 2. How long does it take to do pi over 2? 30 seconds. Then I'm going to end up with an answer in radians per second. Do I want radians per second? No. I want it in radians per minute, so I need to do that unity fraction in terms of time. So I have 60 seconds per one minute. Then I have a cancellation of my seconds. And I end up with pi. And when I get finally done, you all get pi? Yep. So I get pi radians per second. So that's the first answer. So I get pi radians per second, or 3.14 each. The other thing they're asking for is revolutions per minute. So now I have to do the revolutions per minute part. So if I only ask for the radians per minute, I get to stop right there. If I'm asked for the other part, which is the revolutions per minute, I need to take the pi radians, and that should be minutes. Let me go back, that should be minutes. And this is in minutes. I'm going to do the pi radians per minute. I'm going to multiply by my unity fraction. So 1 revolution is 2 pi radians. How many revolutions per minute do I do? 0.5 revolutions per minute. My pi's ends up canceling. I end up with 1 over 2, which is 0.5. So you can write 0.5, or you can do 1/2 revolution per minute. Is there any questions on that?
So 2 pi radians per minute is not how many revolutions you have to do that?
Yep, you still have to do that last conversion. Now, the very last part of this section is linear velocity. If you're looking at your car, it's going to tell you your linear velocity. So if you're looking at your speedometer, that is a linear velocity, and it is doing a conversion based on your angular velocity. It is doing a conversion based on how fast your wheels are rotating. And the assumption is that you are using the tires that your manufacturer wants you to use. So if you are using tires that are larger, you're actually going faster than what your speedometer is. If you are using tires that are smaller, then you're actually going slower than your speedometer says. And that's because on this one, we do need to take into account our radius. So the way that we define our linear velocity is the distance s divided by its time. So that's rate times time equals distance all day long. But now if we convert from velocity, angular velocity, to linear velocity, we know this is s divided by t. But my s, we know from before, the arc length is alpha times r. Now I do alpha times r divided by t. I just rearranged my formula, and I get r times alpha divided by t. But alpha is just, divided by t is just omega, which is my angular velocity. So what I know is to go from linear velocity, it is equal to my radius multiplied by my angular velocity. It is as simple as that. So we go back to our example here. If the blade of a windmill is 30 feet long and rotates 90 degrees for every 30 seconds, what is its linear velocity in miles per hour in the tip of the blade? We've already discovered what this was in our previous example, right? We knew what that was. We knew that omega from our previous example up here was just pi radians per minute. So this is going to be pi radians per minute. I need to multiply that by my radius, and my radius is 30 feet. Now what you do is all of the lovely unit conversions. So I need to go from minutes to feet per minute into miles per hour. So I'm going to convert my time units. So I have 60 minutes in 1 hour. So So there's my time units converted. My next one is my feet into miles. For 1 mile, it's 5,280 feet. And the reason I know that is because I lived in the Mile High City. And there's a place in Denver, actually, where the little stamp that says 5,280 feet above sea level. You all don't care, but useless information. So basically, here's what I'm doing. I am multiplying, and then we'll let you go. So the minutes are going to cancel. My feet are going to cancel. And that's miles over here. I am multiplying pi times 30 times 60. I am dividing that answer by 5,280. Tell me, with your calculators, what I end up with in miles per hour on those windmill blades that you all see in eastern Washington. 1.071 miles per hour. And there we have it. Great. Have a great day. We have finished 10.1.